How was our universe born? And if this seems hard to answer, then how about this? What was before our universe? While scientists are looking for the answer to the most difficult question in history, let's find out what they've come up with so far. In the 20th century, we've shed the light on this mystery, all thanks to this man, Edwin Hubble. One day on Mount Wilson in Southern California, he aimed his telescope at the sky and found out that these random clouds of gas flying everywhere are actually other galaxies, and there are a lot of them. And also, he learned something else, something that changed the world forever. They're moving. So what, you may ask? Well, it meant one very important thing. The universe is expanding. And if it's expanding, then it probably had a beginning somewhere, right? Now, all we have to do is run time backwards and see where the beginning was. It took the scientists many more years to come up with a full-fledged theory, the Big Bang Theory. And here it is. Nothing has ever been anywhere because neither when nor where existed. Do you get it? But actually, no. There was one thing. It was the so-called cosmic singularity, a state of our universe in which it was incredibly small, dense, and very hot. Imagine if our universe was compressed into a small ball. The pressure and temperature inside would be enormous. At some point, it became impossible to withstand them. And here comes the Big Bang. It was an outburst of energy and matter that created everything we see now. Time and space, basic physical forces. It also scattered quarks everywhere. These quarks, tiny particles that make up our world, were all boiling in an incredibly hot cosmic broth. When it cooled down, gravity began to attract them to each other. They gathered into atoms, then molecules, and then into the first objects into the world, stars. And all this happened just some 12 to 14 billion years ago. Alright, now we know how our universe was created, but what was before that? Alan Harvey Guth, an American theoretical physicist and cosmologist, has devoted his whole life to solving this mystery. After learning about the Big Bang Theory, Guth found some flaws in it. For example, the distribution of matter was very even, although it shouldn't have been. Let's hang a balloon filled with paint to the ceiling and lay a white canvas on the floor. If we drop the balloon down, it will burst and we'll see absolute chaos on the canvas. A bunch of spots scattered everywhere randomly. Neither is like the other. But that's not really what the universe looked like. Instead of throwing a colored ball from the ceiling, let's draw a small red dot on the canvas. Now, let's expand it a little more, and capture this all on frame-by-frame shooting. We'll see a circle gradually growing in all directions. That's the reality. The early universe was very even and proportional. That was Guth's discovery, the theory of inflation. Here's what it says. Even before the Big Bang, there was some kind of force that could give the bang a strong acceleration, something that was able to distribute everything in space instantly and evenly. Guth's theory was a success, and now most scientists rely on it. For most of them, this idea of the birth of the universe is quite enough. For most, but not for all. Martin Bojewald is a German professor of physics, and, in his opinion, the universe was born quite differently. Remember when we talked about cosmic singularity? The state of the universe in which it was small, infinitely dense, and super hot. According to Martin's theory, the singularity couldn't just appear out of nowhere. This is nonsense. But then, where did it come from? Let's look at a pendulum on an old clock. The pendulum rotates back and forth. Its movement is smooth, continuous, and non-stop. This is how we usually see time. It flows and never stops. But quantum time, quantum time doesn't work that way. It's more like the second hand of a clock. it consists of small segments and makes short pauses. And, just like with the second hand of a clock, the beginning of one segment of time is always the end of another. See what I'm getting at? Let's go back to balloons again. According to the Big Bang Theory, once upon a time our universe began to expand, inflate like a balloon. But sooner or later it will blow away back. The universe will start shrinking and return to the state of cosmic singularity. And then guess what? The Big Bang too. Nothing appears out of nowhere and disappears into nowhere. According to Braneworld's theory, the beginning of each universe is the end of the previous one. Our universe is not at all the first and not the last. Millions of similar universes existed before us and will exist after us. This theory, although it sounds very logical, is far from complete. Unfortunately, we don't have enough knowledge to find all the evidence for it, so for now, all this is just a hypothesis. But some people come up with even stranger ideas. Scientists promote such unusual theories that no one could even think of. Neil Turok, a South African physicist, and his colleague Paul Steinhardt, an American theoretical physicist, look for answers far beyond our universe. They say that yes, our universe isn't the first one. There have been and will be an infinite number of them. And not only will there be endless Big Bangs, our universe is just one of an infinite number of others. And all of us are stuck in a cycle of endless rebirths of parallel worlds. This sounds incredible and frightening at the same time. But how does it work? According to this theory, our universe is located inside a so-called brane, as in membrane. In other words, we're stuck in some kind of elastic surface that's capable of contracting, stretching, oscillating, and so on. Like pieces of fabric on a rope, these parallel universes are located near each other. Each one has a neighbor. We're not the exception. Another universe may be an inch from ours, but we can't see it. That's because there's a tiny space between us, and this tiny space contains the fourth dimension. How do these universes originate? Through brane collision. These branes are getting closer to each other very, very slowly, until one day they finally collide. Their collision creates two Big Bangs and two parallel universes. Then they're moving away from each other. The created worlds continue to live. We're currently at this stage. But when they disappear, the branes collide again. And this will lead to the birth of a new universe. Remember the inflation theory? There was a mysterious energy that pushed and accelerated the Big Bang. Well, if we did collide with another universe, that would explain everything. Of course, everything described here is a great simplification. When you hear that our world is some piece of fabric on a rope, it sounds like complete nonsense. But this idea is based on string theory and M theory, two giants of quantum mechanics. If they turn out to be true, they could explain almost everything in our universe. Creating a theory is an incredibly huge process. Turok and Steinhardt made a huge amount of calculations and swept away many, many non-working theories. Also, to work this out, they have to overcome the limits of the human mind and think in 11 dimensions at once. Unfortunately, this crazy and elegant idea was laughed at. Turok and Steinhardt say that scientists are regular people, just like everyone else. They're also afraid of change and the unknown. And it's really scary to question everything we once believed in. Many years ago, people didn't believe that the Earth was round. Then they were outraged by the Big Bang Theory. We can't make discoveries without struggle and fear. That's why Turok and Steinhardt don't plan to give up so easily. After all, the evidence that we have now only says that each of the three theories is equally possible. So which answer is correct? We may never know, at least not at this stage of human development. Unfortunately, as long as we have no evidence, we can only theorize. But maybe one day we'll find something that will open our eyes once and for all. Maybe one day we'll solve the mystery of how our universe came to be. Black holes, the most terrifying, mysterious, and fascinating objects in the universe. Eternally hungry, they eat everything in their path and are constantly expanding. But how small and how big can a black hole be? Let's find out. It's not very easy for a black hole to be born. Most often they're just a result of a massive star ending its life cycle. If you take a star and squeeze it very, very hard, at some point it cannot withstand the pressure anymore. So it collapses and turns into a black hole. For example, we can create a black hole by shrinking the Sun to about 1.8 miles, or squeezing the Earth into the size of a pea. Either way, in the end, we get a mysterious, dark object with incredible mass and gravity. Unlike stars and planets, black holes have no size restrictions. They grow when they eat the matter around them, but how much does their size vary? For example, can they be very small? Theoretically, yes. There may be black holes with a diameter of 1 atom, or even less. They're called primordial black holes. They may or may not exist, and if they do, they're probably the oldest objects in the universe, older than the atoms themselves. They would have formed right after the Big Bang, a long time ago when the universe still had an incredible density, a huge amount of energy, and in general was like a boiling broth. Any particle that was slightly denser than its neighbors could form a black hole. And the smallest of them would still weigh trillions of pounds. Those that were the size of atoms would weigh as much as a big mountain, and those that would weigh as much as the Earth could be a little bigger than a coin. But even if they exist, they're pretty harmless. The temperature in them would be so many times hotter than in our Sun, so they would evaporate pretty quickly after their birth. Now let's check out the black holes we know and saw. The first ones are called stellar black holes. Usually, they weigh tens of solar masses, which doesn't seem like much until you remember that the Sun weighs nonillions of pounds. Don't even try to imagine this number. It has 30 zeros. The smallest black hole known to us is about 2 to 4 times heavier than the Sun. It's a lonely hole that wanders through space in search of prey. The one that's closest to us is called Gaia BH1. It weighs about 10 times more than the Sun and can reach many miles in size. And the farthest one is called M33X7. It's somewhere around 3 million light-years away from us, and right now, it's eating a blue giant that's several times bigger than our Sun. Now, let's move to the so-called intermediate mass black holes. You see, just eating a few stars isn't enough. To become larger in size, black holes must either absorb a lot of stars or, more often, merge with another black hole. One of the first intermediate mass black holes that we found was born this way. It weighs 142 times more than the Sun. It's even larger than some counties on Earth. Recently, we discovered 2 black holes in a galaxy 17 billion light-years away from us. One day, they'll merge, but right now these guys are spinning around each other in a crazy dance. And while doing that, they release a crazy amount of energy. It may seem scary, but it's nothing compared to what comes next. Let's move to some serious stuff. Supermassive black holes. Giant, inexplicable monsters that are millions of billions of times bigger and heavier than our Sun. But how did they become so huge? The universe is about 14 billion years old. The black holes grew very slowly, so they couldn't have time to eat so much matter or merge with each other so quickly. So maybe they were also born from the stars? But very, very big ones. Quasi-stars. To imagine their scale, let's take, for example, the red supergiant Stephenson 218. Compared to this star, our Sun is just a grain of sand, even smaller. And Stephenson 218 would be a grain of sand next to a quasi-star. We don't know if they really existed though. They could have formed after the birth of the universe. They could be so big that their core collapsed under their own weight before they even formed. And if that's the case, a small black hole would have appeared in the center of this quasi-star. Now, the frenzied gravity of the black hole held the star together and ate it at the same time. The temperatures were huge, so the star remained stable, and they would live like this for millions of years until the black hole would grow to enormous sizes. Most supermassive black holes are located in the centers of galaxies. You might think that our galaxies orbit around them as we do around the Sun, and that one day we will inevitably all be dragged inside it. But don't worry, that's not the case. Although these guys are incredibly massive, they're not very large in diameter. They can't swallow entire galaxies. For example, in the center of our Milky Way, there's a black hole called Sagittarius A. It has 4 million solar masses, but it's still quite small in size, only 17 times larger than the Sun. And yes, it's still considered small. If we had replaced the Sun with this black hole, it wouldn't even have reached the orbit of Mercury. Sagittarius A is actually pretty nice and calm. Yes, it still swallows giant stars, but it's definitely not a threat to us. But not all of them are like that. For example, a black hole in the galaxy BL Lacertae devours a huge amount of gas and dust. If we were somewhere near it, it would look 115 times larger than the Sun, and we would have burned up just getting close to it. Do you remember that first black hole we ever captured in a photograph? It's located in the Messier 87 galaxy, and it may look small and cute in the photo, but in reality, it's capable of absorbing our entire solar system up to the Orion Belt, and even further. Well, now that we've discussed the terrifying size of supermassive black holes, it's time to move on to the real titans of the universe. Ultramassive black holes. Terrifying, unimaginable giants. The largest objects that have ever existed and probably will exist in our world. Their masses exceed the mass of the Sun by tens of billions of times. Their gravity becomes so strong that they create quasars around them. Disks that shine brighter than thousands of galaxies combined. Remember, we talked about the fact that supermassive black holes aren't able to eat galaxies? Well, these guys devour not only their host galaxies, but literally everything on their path. The ultramassive black hole at the center of the galaxy OJ287 has 18 billion solar masses. It's so gigantic that it has another black hole orbiting it. It would also easily fit not one, but 3 solar systems inside of it. And now, finally, we've come to the largest object in the entire universe. TON 618. The almighty destroyer of worlds. A black hole that has eaten far more than one galaxy. Its mass exceeds 66 billion solar masses, and it could fit 11 solar systems inside of it. The quasar around TON 618 shines brighter than 100 trillion stars. Its light is so powerful that it has even reached us, even though we're at a distance of 18 billion light-years from it. And the creepiest part is, this isn't even its true size. This is what it looked like around 10 billion years ago. Since TON 618 is so far away, its light reaches us for a very long time. That means what we see is how this black hole looked after the universe was born. But what does it look like now? We have no idea, but it's probably millions, billions of times bigger.
During the recent years, scientists made 2 breakthrough discoveries about our universe. Thanks to new technologies, we've looked into the distant past. And we've learned something that can change our understanding of the universe forever. What are these discoveries and what do they mean to us? Let's find out. Recently, we unveiled the first color image from the James Webb Space Telescope. It's a mind-bending photo capturing thousands of ancient galaxies. This oldest documented light in the history of the universe dates back over 13 billion years. That's just 600 million years after the Big Bang. It's like getting a sneak peek into the universe's baby album. But that was just the beginning. Astronomers were expecting to see some tiny young galaxies, but what they found was a real surprise. Impossibly early, impossibly massive, and all that from just a tiny red dot. The lead author of the study, Ivo Labe, was working at the computer as usual, and suddenly he got two numbers. Age, 13 billion years. Weight, 100 billion stars. When he realized what that meant, he nearly spit out his coffee. But that red dot was just the beginning. The next day they found 5 more galaxies just like this. Turns out, these 6 massive galaxies are as old as the Milky Way itself. The entire research team was in disbelief. They were like, wait, what? These guys couldn't be that mature so early in time. Did we make a mistake? But nope. The James Webb Space Telescope, the new cool guy on the space block, just has some serious skills. It can see through dust clouds with its infrared vision and spot galaxies that were previously invisible. Move over Hubble. There's a new stargazer in town. But why is it shaking things up so much? Because this discovery affects our understanding of how galaxies formed. Let's try to explain. A long time ago, 13.8 billion years ago to be precise, our universe was born. It was chilling out for a while, and then it started to form the first galaxies. And these galaxies were full of gas and dust. Eventually, this gas started turning into stars. Some galaxies were more massive and had more stars, and some were lighter and had almost no stars at all. In any case, they all grew gradually. The stars in them were born slowly and smoothly. That's how our current models explain this. But these new observations from the James Webb Space Telescope show an unexpected surprise. Looks like, even in the early universe, our ancient friends had lots of stars. More than what we would ever expect. If that's the case, then these galaxies are like the overachievers of the universe. They skipped the small and gradual growth phase and went straight to being giant universe breakers. According to our current cosmological model, they shouldn't even exist. But they do, so it looks like after the Big Bang, the stars were forming much faster than we thought, which is pretty weird. This could mean that there's something missing in our understanding of the galaxy formation. As you can see, these universe breakers are really living up to their name, causing a potential total consensus among scientists. The universe was like, hey, I'm about to flip cosmology models upside down. But let's not jump to conclusions. There are many theories that could explain these mind-boggling discoveries without breaking the standard model. For example, maybe the light we're seeing isn't coming from stars at all, but from the swirling disks of doom around supermassive black holes. These colossal cosmic beasts can gobble up matter and spit out a dazzling light show. And James Webb Telescope's keen eye is picking up on these enigmatic accretion disks like never before. Or maybe these galaxies could be playing hide-and-seek with us. Maybe there's more to the story that we haven't seen yet. After all, the universe is vast and mysterious, and we've only just begun to scratch the surface. And whoa, we really need to slow down here. Before we even try to explain all this stuff, we need to confirm whether these ancient galaxies really are that old. Although even if they're actually just supermassive black holes, it still shows an astounding change. We'll have to wait about a year to find out. One thing's for sure, the James Webb Space Telescope has definitely taught us a valuable lesson. Expect the unexpected. And this is just the beginning of unexpected. Ivo Labe's team wasn't the only one who made such a huge breakthrough. There's also a team that claims that they've unlocked the secrets of the universe's past, and that's worth 2 Nobel Prizes. Move over James Webb Space Telescope, because this discovery came from an antenna that's smaller than a fridge and costs less than $5 million. Talk about space bargain hunting! The astronomers caught this signal that showed some surprises. It was coming from the earliest stars of our universe, back in the days when they were just beginning to twinkle. Say hi to our celestial ancestors again. Now, the signal was pretty weird. The temperatures were unusually low, and there was a pronounced wave that left astronomers scratching their heads. What could be causing all this? Well, there's a theory. Dark matter may have been at work, and if that's the case, then we can really be on the verge of a great discovery. Imagine you're looking at the night sky filled with stars, but there's something else there that you can't see. It's like an invisible cloak that covers the entire universe. Scientists call this mysterious stuff dark matter. Dark matter is like the ghost of our world. It doesn't emit, absorb, or reflect any light. We can't see it with telescopes or our eyes. That's why we call it dark matter. But if we can't detect it in any way, how do we know it exists? Because of its gravitational pull. One day we noticed that our understanding of how galaxies were created was incorrect. According to our calculations, they should have been some chaotic gas, but something held them together, turning them into spirals, like some kind of invisible glue. Then we thought, maybe this invisible glue really exists. If the moon was invisible, we would still suspect that it exists somewhere because its gravity affects the tides on Earth. This is also the case with dark matter. Its gravity influences the motion of galaxies and other cosmic objects. In fact, dark matter makes up a huge chunk of the universe, about 27% of it. Moreover, the normal matter we can see, like stars, planets, and galaxies, only make up about 5% of the universe. So even though we can't see dark matter, there's actually more of it in the universe than everything we can see. Scientists are still trying to figure out if dark matter exists and what it can be made of. Some theories suggest that it could be made up of exotic particles that are different from the particles that we're used to. Others think that it might be some kind of weird, undiscovered form of matter that doesn't interact with light at all. Anyway, it's an intriguing mystery, and if we ever confirm the existence of dark matter, our understanding of our world will change forever. So now you can understand why the excitement in the scientific community is palpable. If this discovery is confirmed, then we will get the first real proof of dark matter. This discovery may be even more important than the Big Bang itself because, as astronomers put it, we are made of star stuff, and so we are glimpsing at our origin. But of course, we still have to wait and explore all this in great detail. In science, one should never rush to conclusions. And while scientists study this stuff, we'll be here, on the edge of our seats waiting for the next space blockbuster to unfold. The universe never ceases to amaze us with its wonders. Who knew that such a small and humble antenna could unlock such cosmic secrets? It just goes to show that in the vastness of space, even the tiniest discoveries can have the biggest impact. Keep looking up, and who knows what other cosmic surprises are waiting to be uncovered.
So you're driving down the highway, and an 18-wheel tractor-trailer is coming up fast behind. You've got to change lanes. You look in the mirror. Is there enough space? And you notice the words on the mirror. Objects in the mirror are closer than they appear. No kidding! Well, it's the same with the Milky Way galaxy. There's another galaxy headed this way, and like the tractor-trailer, it's closer than it looks. The Andromeda Galaxy, or M31, as it was labeled originally by Charles Messier in his catalog of 110 fuzzy objects in 1774, is now officially named NGC 122, that's New Galactic Catalog 122. A spiral galaxy larger than the Milky Way, the Andromeda Galaxy is so big and so close that you can see it without a telescope. In fact, it appears with the unaided eye half as wide as the Moon. It's estimated that the Andromeda Galaxy contains 1 trillion stars, compared with the Milky Way's estimated 300 to 400 billion measly stars. To see the Andromeda Galaxy, you must allow your eyes to become dark adapted. This might take about 10 minutes while your pupils dilate to take in as much light as possible. M31 is best seen from late summer through winter, when the great square of Pegasus the Winged Horse is overhead. Draw a line across the great square diagonally upwards from the lower corner star, then go a little further beyond the square. There it is! But you still won't be able to see how big it is, unless you peek at it from the corners of your eyes. If you stare straight at it, the galaxy will tend to fade away. You must use your peripheral vision to see how big the Andromeda Galaxy appears. Peripheral vision, or averted vision, allows you to see light more sensitively at night, but without color. Sailors have used averted vision for centuries to see faint lights out on the ocean or on land. Aristotle used averted vision to observe star cluster M41 in Canis Major, as he described in his book Meteorologica. In a telescopic photograph, the Andromeda Galaxy appears 6 times wider than the Moon, because with the unaided eye, we can only see the bright center of the galaxy. A telescopic photograph shows how massive M31's spiral arms really are. And this beast of a galaxy is headed our way. We are looking at a future massive collision of galaxies of, well, galactic proportions. When that happens, humanity may need to relocate to another galaxy to inhabit. Perhaps we'll go to the Pinwheel Galaxy in the asterism of the Big Dipper. How do we know the Andromeda Galaxy is moving towards us? With a tool called a spectroscope. After the camera, the spectroscope is the most important attachment to a telescope. Oh, except for the human eye. Our eyes only see light. You don't have this big horse in your eye. You only have the light being reflected by the horse in your eyes. The same with space. We only see the light coming from there. So, if we are going to understand space, we need to understand light. And that was not an easy task for astronomers of the 19th century. The invention of the spectroscope was a big breakthrough in understanding light coming to Earth from space. With a spectroscope, astronomers can tell which direction objects in space are moving, as well as which elements are making the light. When you hear an ambulance approaching, you hear the siren getting louder and higher, and when it passes you and goes away, you hear the siren's sound get weaker and lower. The change in pitch frequency depends entirely on the motion of the source. This is called the Doppler effect, after the Austrian physicist and mathematician Christian Johann Doppler, who first explained the effect in 1842. The ambulance siren is not changing its volume. The sound waves are being compressed as it is approaching and stretched as the ambulance recedes. The spectroscope shows that light waves show the same Doppler effect as sound waves. They are compressed as the star or galaxy is approaching us and appear stretched when it is receding. Therefore, the light from an approaching galaxy will appear slightly bluer, the blue shift, a slight increase in frequency, and the light from a receding galaxy will appear slightly redder than normal, or red shift, a slight decrease in the light's frequency. In 1929, Edwin Hubble, after whom the Hubble spacecraft is named, published his spectroscopic study of 46 galaxies, the light from all but one of which was redshifted, moving away. Hubble's study provided the first evidence that the universe was expanding. The farther away a galaxy was from the Milky Way, the faster it was moving away. This was also the first evidence that the universe began with a Big Bang. The one galaxy whose light was blue-shifted, moving towards the Milky Way, was M31, the Andromeda Galaxy, the closest galaxy. 250,000 miles per hour seems a pretty high speed at which to have a collision. That's the speed spectroscopic measurements of the blue shift of Andromeda indicate. It's going to be a big mess when it happens. But when is it going to happen? To determine when the two galaxies will collide, we need to determine the distance between them. And for that, we need, boom, supernovas. Type 1a supernovas are what are called standard candles. Just as we know how bright a candle shines, we know how bright a Type 1a supernova shines, its absolute magnitude. A Type 1a supernova appears when a white dwarf collapses under the pressure of all the gas it has been gravitationally slurping from a companion star. Looking at the Andromeda Galaxy and measuring the apparent brightness of a supernova in the galaxy, it is possible to calculate its distance away from us. Because the intensity of light dims inversely with the square of its distance away, which is called the inverse square law, by comparing the apparent brightness of a supernova in the Andromeda Galaxy with its absolute brightness, well, we get an approximate distance of 2.5 million light-years. Since 1 light-year is approximately 6 trillion miles, and the Andromeda Galaxy is 2.5 million light-years away, even though it is approaching at the speed of about 250,000 miles, we have about 4 billion years before the big collision. So you can wait until after lunch, maybe dinner, to start packing. As an aside, if we see the Andromeda Galaxy as it was 2.5 million years ago, and it has been moving toward the Milky Way all this time, how big in the sky would it appear now? Quite as big as that tractor trailer in your rearview mirror. But do we really have 4 billion years before the galaxies crash? There are several other factors to consider. The minor galaxies that are gravitationally linked to both the Milky Way and the Andromeda Galaxy will be swallowed up by their host galaxies. Considering the lopsided mass distribution that will result, the galactic collision of the Milky Way and Andromeda will be affected. Some scientists are saying it won't be a direct hit, but more of a side swipe. And then there's the galactic halos of each galaxy. Here's what Project Amiga has found out about the halo of stars and gas surrounding the Andromeda galaxy. Using the Hubble Space Telescope, researchers were able to observe how the light from bright distant quasars were being absorbed by the mostly invisible gas around the Andromeda galaxy. Look at the results. Notice M31 in the center. If the same is true of the Milky Way, and there's no reason to think it would be different, then the halos of the two galaxies are touching now. The collision has already begun. There is also a question about what effect the dark matter clouds around each galaxy might have on an impending collision, or are having now. But enough of speculation. In 4 billion years, the Sun will have increased brightness on its way to becoming a red giant star. And humans will have already found another galaxy to inhabit. Happy traveling, dear humans! You fly away from Earth at a safe distance in your super modern spaceship, and then BAM! You travel faster than the speed of light in interstellar space. How cool! The light from thousands of stars rushes past you. A few minutes, and you're on the other side of the Milky Way and going to work. Such travel has long been common for humans, for you are a member of the human civilization that has conquered the entire galaxy. But it took almost 90 million years to get there. So how did we achieve this? It's like a computer game. In the beginning, we had a fleet of 3 motherships that could travel at 310 miles per second. Each of them had 10 colonization pads. The ship could undock a pad and drop it on the desired planet. We also had 2 speed ships that traveled twice as fast but could only colonize one planet. Each colonized planet could send 1 new ship on an expedition. So humanity was able to spread across the galaxy in 90 million years. Most of that time was spent flying from star to star. So the main problem of colonization is speed. Year 2021. Our spaceships can now fly at about 24,850 miles per hour. That's enough speed to travel from New York to Los Angeles in less than 4 minutes. But a trip to neighboring planets like Mars still takes about 7 months. The nearest star to the Sun, Proxima Centauri, is 4.2 light-years away. That means light, the fastest thing in the universe, takes 4.2 years to get there from the Sun. It would take our rocket 73,000 years to get there. That's longer than an advanced human civilization has existed. And our galaxy, the Milky Way, is 105,000 light-years wide. So even traveling at the speed of light would take forever. So, naturally, humanity came up with other ways to travel. Let's move into the future and imagine that we've solved this problem. We started accelerating with microscopic probes propelled by a directional laser beam from Earth. This made it possible to reach speeds of 25% of the speed of light, still very slow. The problem was that nothing that has mass can travel at the speed of light. So we moved on to the Alcubierre drive study. This method doesn't involve moving from point A to point B, but instead compressing the space between those points. Here's a piece of checkered paper. Imagine that you need to travel 3 squares to your destination. Instead of moving in a straight line as fast as possible, we squeeze these squares so that our spaceship is at point B. Now we unsqueeze them back. Space is normalized and we've traveled, in fact, standing still. This is how the Alcubierre drive works. It compresses space in front of the spaceship and expands it behind its tail. So, theoretically, an Alcubierre drive spaceship can move at any speed, even faster than the speed of light. But the amount of energy needed to do this is enormous, and it could be compared to the mass energy of the entire planet of Jupiter. So, while some scientists were working to improve the Alcubierre drive, others were looking inside the most mysterious object in the universe, a black hole. A black hole is something so heavy that it attracts even light and won't let it go. Imagine a circular trampoline. This is our space-time. We put a basketball in its center. The trampoline sags a little bit. Now all the objects we put on the trampoline will roll toward the basketball. That's how gravity works. But if you roll the golf ball past the basketball, it has a chance of getting out of this funnel. Now put a heavy bowling ball in the center of the trampoline. The trampoline sags even more. Now the golf ball will inevitably fall into the funnel with the bowling ball with no chance of escape. That's how a black hole works. And some scientists believe there may be a wormhole at the heart of a black hole. It's a shortcut between point A and point B in the universe. Back to our piece of paper. Instead of moving straight ahead, we fold the piece so that point A is right above point B. Now we make a hole in the paper and move to point B. We unfold it back and voila! You've arrived at your destination. So there's a theory that if a spaceship enters the black hole's gravitational field and withstands the incredible stress there, it can exit to any other point in the universe which that wormhole led to. It might even be another galaxy, or even a parallel universe. Well, our research was successful, and now, looking at a map of the Milky Way, we can get to absolutely anywhere. All that remains is to choose the right place to colonize. There are about 1 billion stars. Around each of them are planets possibly suitable for life. So we need to narrow down the list. First, we look for relatively young stars, almost like our Sun. Near them, a human colony can potentially live for a long time. After that, when a star gets old, it begins to expand and turn red. In the last stages of its life, it can absorb all the planets around it and then explode with such force that the light from the explosion can be seen dozens of light years away. Secondly, the candidate for a human colony must be in the habitable zone of the star. It's a sweet spot, not too far away from and not too close to the star, so that it's not too cold or too hot there. In other words, water on the planet must exist in liquid form. Also, the candidate planet must have a solid surface so that we can live on it. Another important factor is the size of the planet. If it's too big, its gravitational force will press on us. It'll be harder for us to jump, walk, and lift weights on this planet because we're used to the Earth's gravity. But if the planet is too small, we'll feel like real strongmen there. We'll be able to jump high and lift large weights. But then our muscles will lose tone and our health will deteriorate. So, we're looking for a planet about the size of Earth. Altogether, we have about 100,000 star systems that fit our parameters, so we start exploring and colonizing. And here's our first target. We've named this planet New Home. Clever. We fire up our faster-than-light engine, and bam, we're there. Even though this planet fits all our criteria, it's still hard to call this place home. Desert landscapes with lots of craters and canyons. We'll have to work hard to make this place look like Earth. The terraforming phase of the planet is about to begin. That means we're going to change the climate and the atmosphere here. We need about 78% nitrogen and 21% oxygen so we can breathe here without spacesuits. So we're launching air plants. Other plants will produce water. We're also building power plants and a plant to produce fuel for our spacecraft. Last but not least, food extraction. Once everything is ready, the colony here can exist on its own. And after several centuries, this planet will be developed and populated enough to send an expedition to colonize neighboring worlds. So, for many millions of years, humanity has been weaving its web in the Milky Way. From one planet to another, we've colonized our galaxy. Humanity is now not only multiplanetary, but also interstellar. The next goal is to make us an intergalactic species. Here's our Milky Way. Zoom out. This is the local group of galaxies. Each one contains millions of stars, candidates for colonization. We have to travel 5 million light-years to get there. Zoom out again. Virgo supercluster. There are about 100 clusters of galaxies similar to our own. Zoom out again. Billion light-years from our home. Neighboring superclusters. Now, each galaxy looks like a little dot, and there are thousands and millions of them. Zoom out even more. 14 billion light-years from Earth. This is our observable universe. There are about 2 trillion galaxies. Even at 1,000 times the speed of light, it would take us billions of years to colonize even 1% of the stars here. But it's not over yet. There's a cold spot on the map of the observable universe. Some scientists think it's a scar from a collision of our universe with a neighboring one. They say the universes could be like bubbles, each containing trillions of galaxies. Once such bubble crashed into ours, and its gravitational force ripped clusters of galaxies out of our universe. If this is true, then parallel universes do exist. Then we have truly endless possibilities for exploration, finding new worlds for humanity, and contact with extraterrestrial civilizations. Sounds like fun.
In the heart of the galaxy, there lies a mysterious object, the likes of which no astronomer has ever seen. It streaks across the sky like a shooting star on caffeine. So, what is this mysterious blob? And how is it related to the black hole in the center of our galaxy? Let's find out. This thing is called X7. It's the mysterious blob that's been hanging around our galaxy's supermassive black hole for decades. Some even say it's been lurking around there for, like, hundreds of years. We know a few things about X7. For example, it weighs around 50 times as much as Earth. It may sound like a lot if you're an Earthling, but in space, that's like a tiny drop in the ocean. X7 is also moving pretty fast, at speeds of up to 700 miles per second. That's faster than you trying to catch the last slice of pizza before your roommate gets to it. But what in the world is this thing? A magic star we've never seen before? An extraterrestrial spaceship? Well, there are some theories connected to the blob's future tragic fate. Unfortunately, X7's days are numbered. Right now, it's on a 170-year-long elliptical orbit around the supermassive black hole at the center of the Milky Way. But it's not going to make it that far. Each year, it's spiraling closer and closer to the black hole. In just a few years, it will become spaghettified. Yes, that's a real scientific term. And finally get sucked in, never to be seen again. There are supermassive black holes in the centers of all galaxies, including our very own Milky Way. These black holes are so massive that they warp space-time, causing nearby stars to orbit around them at incredible speeds. They serve as cosmic vacuum cleaners that suck in anything and everything that comes close enough. The black hole in our galaxy is called the Sagittarius A star. Sounds like the name of a fancy Hollywood celebrity, doesn't it? But this celestial object is far more impressive than any mere mortal. It's about 4 million times more massive than our sun, which means it could probably eat our entire solar system for breakfast. But don't worry, these black holes may seem really scary, but in reality, they're too small to compete with an entire galaxy. They'll just suck in a couple of the nearest stars, and that's all. Also, Sagittarius A star doesn't seem to have a very good appetite. It's been observed to be pretty quiet lately, which is good news for us. But even if it were super greedy, it wouldn't pose any threat to us. This black hole is over 26,000 light-years away. From Earth, we can see it in the Sagittarius constellation. In 2022, the Event Horizon Telescope collaboration released the first ever image of Sagittarius A star. It took years of collaboration and technology to capture this stunning image. And this is our second photo of a black hole in history. The first one was released in 2019, and it showed the supermassive black hole called M87 star. Yes, they both have star in their names. Don't try to make it make sense. Anyway, you may remember this photo as the first ever image of a black hole ever. It went crazy viral across the internet. And this black hole, M87 star, located in the Messier 87 galaxy, is way scarier than Sagittarius A star. You thought 4 million solar masses is impressive? Then how about 2.5 billion solar masses? M87 is a real monster. It's also known for its powerful jets of plasma, which are so energetic that they extend thousands of light years from the black hole's center. If M87 were a superhero, it would be Iron Man, with his repulsor beams on full blast. Now technically, you can't take a photo of a black hole itself, since it's, well, black. No light can escape its grasp. But the glowing orange ring in this photo shows the matter surrounding Sagittarius A star. It's called the accretion disk, a swirling disk of hot gas that spirals the center, heating up to millions of degrees in the process. It's like a giant fiery vortex, but with no escape. And the shadow in the center indicates the black hole itself. Inside that shadow, there's an event horizon. The event horizon is the boundary around the black hole, beyond which nothing, not even light, can escape its gravitational pull. It's the point of no return, where the gravitational force is so strong that even the fastest object in the universe, light, can't escape. Once you cross the event horizon, you're doomed to fall toward the center of the black hole, where the laws of physics as we know them break down. And this is exactly the fate that awaits our unfortunate X7. Right now, The pure blob is getting stretched and yanked by powerful tidal forces. By the way, before it meets its untimely demise, X7 is expected to put on a bit of a show. Its closest approach to the black hole, called periastron, is projected to happen in 2036. And when it finally gets torn apart by the Sagittarius A star's gravitational forces, there may be some cool fireworks to see. But this is not the most important thing. The funny part is, X7's future end may help us finally understand what the heck even is this thing. A team of scientists have been studying how a strange blob orbits the black hole. And that's when they discovered that X7 has stretched to almost twice its initial length. And what does that mean? Well, it suggests that X7 is most likely made of debris ejected during a recent collision between two stars. Yep, you heard that right, a space car crash. Imagine this. Two stars fall in love and start circling each other for many years. After that, they finally merge together. At this moment, they eject tons of gas and dust. And perhaps this cosmic dance created our blob baby, X7. It's basically like the crumbs left on the table after a giant space feast. Something like this is actually pretty common, especially around black holes. It's like a galactic fender bender that sends debris flying everywhere. Actually, the universe is full of mystery blobs. They're called the G objects. No, they're not the G-men from Men in Black, but they're just as mysterious and elusive. These guys have been puzzling astronomers for more than 20 years. They look like gas clouds, but behave like stars. It's like they can't decide whether they want to be a cloud or a star. Come on, guys, make up your mind. G objects stretch out at the closest point to the central black hole, but emerge intact, like a rubber band that stretches but doesn't break. Scientists think that they're the stars that have merged together into one. And while doing that, they also produce a huge cloud of gas that hides the result from view. Kinda like when you're wearing a bulky sweater, so that no one knows that you've put on a few extra pounds. And then a study published in 2021 found that one of these objects, G2, was actually a molecular cloud concealing 3 baby stars. Talk about a plot twist. But X7 is the black sheep of the strange blob family. It's significantly different from the G objects, like the weird cousin you see once a year at family gatherings. Its evolution has been more dramatic. Also, it's not being held together by a mass lurking in its center. So what is it being held together by? Pixie dust? Magic? We need answers! That's why scientists believe that X7 isn't a G object itself, but debris left from it. Or maybe not. We have no idea. The possibilities are endless, and that's what makes astronomy so exciting. So let's keep our eyes on the skies and see what other strange objects are out there. Who knows? Maybe we'll discover another mystery blob, and this time it's going to be a spaceship. Now that would be awesome.
They aren't supposed to exist. No one expected to find them. Scientists can't explain how they formed. And still, the James Webb Space Telescope has found them. These 6 galaxies, as massive as our home Milky Way, are full of mature red stars. They're so far away from us that they look like tiny reddish dots, even to this extremely powerful telescope. Astronomers have analyzed the light coming from these galaxies and estimated their age. They appeared 500 to 700 million years after the Big Bang. So far, nothing surprising. Galaxies that young aren't exactly rare. Scientists think that our first star clusters could have sprung up soon after the universe left the so-called Dark Ages. Those were the first 400 million years of its existence. At that time, only a thick fog of hydrogen atoms filled the cosmos. What is extremely bizarre about these galaxies is their tremendous size and the age of the stars inhabiting them. But this doesn't coincide with the existing ideas about what the universe looked like and how it evolved in its early years. Plus, it doesn't match with earlier observations made by the Hubble Space Telescope, Webb's less powerful predecessor. So, according to scientists, what are early galaxies supposed to look like? The answer is simple: young and small. And indeed, previously, most early universe galaxies we found were just space babies, blue and small. They seem to have appeared out of the primordial cosmic soup just recently, and were still building their early stars and other structures. Most young stars are actually blue. As they age, they acquire a reddish glow after burning through their star fuel and cooling down. That's why astronomers were not ready to see old red stars in those ancient galaxies Webb telescope was built to discover. Another thing they weren't ready to spot was galaxies more massive than 1 billion suns, and still, it happened. The most massive galaxies discovered recently seem to have masses just twice or 4 times lower than that of the Milky Way. And the most astounding thing here is that these galaxies were already that big when the universe was a mere 3% of its current age. But before astronomers start rewriting their theories, trying to explain how such huge galaxies formed so fast after the Big Bang, we need to make sure that what we're looking at isn't some other space phenomenon. Even so, most alternative theories need totally new concepts as well. One of them goes like this. Perhaps stars in the early universe emit light in some unusual, exotic way. And since astronomers didn't know about it, they didn't include this possibility in their models. Or our understanding of how stars form might be inapplicable to the early universe. If any of these theories turns out to be true, it'll overturn our understanding of star formation altogether. Now, how about we talk about the device that helped astronomers to discover those bizarre galaxies? The James Webb Space Telescope is an absolutely stunning piece of equipment, which is around 100 times more powerful than the Hubble Space Telescope. And the latter has observed places that are 13.4 billion light-years away. The James Webb Telescope is also on the pricey side, to put it mildly. Even though originally, the cost of the telescope was estimated to be just $1 to $3.5 billion. The whole development process cost around $10 billion. For comparison, it cost NASA $4.7 billion to build and launch the Hubble telescope. It was another $1.1 billion to fix it in orbit. Even though the James Webb Space Telescope itself is 3 stories high and the size of a tennis court, its mirrors are the lightest large telescope mirrors of all time. During the manufacturing process, they underwent a 92% reduction in weight. When you look at them, the telescope's mirrors seem to be gold, but in reality, they're made of beryllium. This is a steel gray, lightweight, and brittle metal. A gold coating is applied to each mirror, that's true, but they can't be produced entirely out of gold, since this precious metal tends to expand and contract, even with small temperature changes. So, the total amount of gold in the James Webb Space Telescope is less than 2 ounces. That's a golf ball-sized piece of gold. And the gold plates covering the mirror are only 1,000 atoms thick. As for the telescope's abilities, it would be able to clearly see a US penny from 24 miles away and a football from 340 miles away. James Webb's telescope side is cooling itself down, and its temperature doesn't rise higher than negative 370 degrees Fahrenheit. That's cool enough to make liquid nitrogen. A truly enormous 5-layered sun shield surrounds the telescope and reflects away as much sunlight as possible, letting the telescope stay cool. JWST is believed to be able to detect water on distant exoplanets. For a long time, astronomers have been discovering planets orbiting stars outside of the solar system, by monitoring slight dips in stars' light. Such dips happen when planets pass in front of them. Plus, it's possible to read unique signatures in the light. This can tell us about a planet's chemical composition. And the strongest and most readable signatures happen within the infrared spectrum. And guess what? James Webb has state-of-the-art infrared instruments. They can help scientists spot new planets and even identify the presence of water there. The telescope was launched near the equator because Earth spins a bit faster there. And this gave the rocket some extra push. When the James Webb Space Telescope runs out of fuel, it'll keep orbiting the Sun indefinitely. On the other hand, even though the telescope wasn't actually designed to be serviced or upgraded, it might potentially be refueled with the help of robots. This would extend its lifespan. Interestingly, at first, astronomers were sure that finding something exciting with the help of James Webb would take time. They thought that the first discovered galaxies would be so small and dim that the telescope would only find some remote candidates at best. But it didn't go as planned. As soon as the first images were released, scientists started finding countless galaxies, bright, large, and impressively old. The competition is still on. One research group after another spots new record-breaking worlds. One astronomer even said that the scientific world was freaking out since no one had actually expected such impressive results. One of the main goals of the Webb telescope is to observe the light from the very first stars and galaxies in the universe. Unfortunately, the farther away an object is, the faster it's moving away from us. And the longer the light has to travel, the more it stretches towards the infrared side of the spectrum. This is called redshifting in astronomy. But thanks to its infrared equipment, James Webb can reveal previously invisible worlds to us. So, thanks to this telescope, we've managed to see incredibly distant galaxies that were born around 3.8 billion years ago. It means that the light JWST detected took more than 13 billion years to reach Earth. Can you imagine that? But one of these galaxies stands out from the rest. It appears to be the oldest galaxy astronomers have discovered so far. It's called Glass Z13, and it dates back to a mere 300 million years after the Big Bang. The previous oldest galaxy scientists identified was found by the Hubble Space Telescope, and it dates back to 400 million years after the Big Bang. During that scarcely probed era, the very first galaxies and stars started to appear. But how exactly did this process unfold? No one knows for sure, yet. It might have depended on the laws of some exotic physics, including the influence of dark matter and dark energy, or some poorly investigated communication between gas, dust, and starlight. With the help of the Webb telescope, scientists can now test their theories about what was happening out there after the birth of the universe.